Topic 5.2, heating effect of electric currents. We have essentially Ohm's law. It's represented here as resistance is equal to voltage divided by the current. R is resistance. It has units of ohms. That's capital omega. V has units of voltage or volts. I has units of amperes. I is current. We have these equations for power. Power is voltage times current, or it's current squared times resistance, or it's voltage squared over resistance. Total resistance in a series circuit, so say I have a bunch of resistors wired in series, wired in a line, you can just add up the value for each resistor to get the total resistance. For resistors wired in parallel, we use this equation. You invert the value for each resistor first, you add up all of those fractions, and then you have 1 over the total resistance, and you end up inverting that sum. This equation is the equation for resistivity. Rho is the symbol for resistivity. It depends on, it's proportional to the resistance of that material. To the resistivity, and that's equal to the resistance times the cross-sectional area of the conductor divided by the conductor's length. Okay, so if you've ever looked inside of an electronic device, you have seen resistors. A large resistors I have in the classroom will look like this. Resistors on your circuit boards or inside your computers will look smaller, but essentially the same appearance. Resistors work because they're made of carbon on the inside. Carbon is a semiconductor. Less carbon there is, the harder it is for current to flow through the resistor. As the animation shows, carbon is spiraled away to cut down the cross-sectional area. This increases the resistance to whatever value that is desired. Some resistors are very precise and made of wire. These are called wire-wound resistors. Some resistors can be made to vary their resistance by tapping them at certain places. These are called variable resistors and potentiometers. So by tapping, I mean you can effectively shorten the length by choosing different places to attach your conductor. Thermistors are temperature-dependent resistors, changing their resistance in response to temperature. Light-dependent resistors, LDRs, change their resistance in response to light intensity. Resistance is just a measure of how hard it is for current to flow through a material. It's measured in ohms, and you can measure it using this ohm meter. So let's say we can attach the ends of these leads from an ohm meter to a resistor. When we turn the dial, we might see this, a reading of 0L. This just means that the resistance is too high to record with the meter. Maybe we need to change the dial or the scale we've chosen for the read. So we can switch the scale, change the resistor, and let's say we get a read of 330.4, and this would be ohms. So in the front of your data booklet, you'll see various schematics. We have a fixed resistor, which has 2 leads, the schematic for the variable resistor, which has 2 leads and arrow. The potentiometer looks like this with 3 leads. Thermistors have 2 leads and this symbol in the middle. And again, as temperature increases, the resistance decreases for these types of resistors. We have the LDR. It looks like 2 leads with 2 rays of light hitting the resistor. And as brightness increases, resistance decreases. These resistors are used in different types of sensors. Okay, so resistance, again, is calculated by dividing voltage by current. Units are ohms, and resistors, fixed resistors, you can read using the resistor color codes provided by the manufacturers. For example, if I was to read this from left to right, I would get a value of 3, because it's orange, 3, brown is 1, and yellow is 4. So 3,314 ohms. But if you ever end up working with resistors or doing anything with electrical engineering, it will be very clear. You can only read the resistors in a particular order, or else you're going to get numbers that the manufacturer didn't make. So there's only really one way to read the resistors. So metaphors can be useful for understanding these concepts like resistance. So let's consider two identical milkshakes shown. In the first experiment, the straws have the same diameter, but they have different lengths. So you can see it's easier to drink the milkshake from the right glass. So again, resistance is a measure of how hard it is to pass something through a material. Resistance then is proportional to length. In the second experiment, we'll keep the lengths the same, but this time we change the diameters. As shown, it's much easier for the milkshake to be consumed when the diameter is large. Therefore, the resistance is proportional to 1 over the cross-sectional area of the straw. Cross-sectional area, let's say I'm looking at this straw on end. This would be the cross-sectional area. So even through solids, resistance is proportional to length over the cross-sectional area. R also depends on the material through which the electricity is flowing. Different materials, different metals, different compounds have different crystalline structures, different reduction potentials, etc. It makes it harder or easier for the sea of electrons to flow through them. For example, the exact same size of copper will have much less resistance than carbon. With the proportionality constant rho, we have an equality. Resistance equals rho, which is resistivity, times the length divided by the cross-sectional area, or the resistivity equals resistance times the cross-sectional area divided by the length. The Greek rho is resistivity measured in ohms times meters. This German guy, Ohm, studied resistance of materials from the 1800s to 1826, and he stated, provided the temperature is kept constant, the resistance of very many materials is constant over a wide range of applied potential differences, and therefore the potential difference is proportional to the current. This is known as Ohm's law, and it has this equation, V is equal to I times R, Ver. By the way, Ohm's law applies to components with constant resistance. Materials are considered ohmic if they behave according to Ohm's law. In other words, the resistance stays constant as the voltage changes. A lot of materials aren't ohmic, however. So you can see this would be a non-ohmic material, ohmic in the middle, and then not ohmic on the far right. Okay, remember that power is the rate at which work is being done. Power equals energy over time or work over time. And we learned from topic 5.1 that work is equal to charge times the voltage. Thus, power equals work over time, or power equals QV over T. Factor that out. Q over T, that's current, so PIV, power equals current times voltage. This power represents the energy per time delivered to or consumed by an electrical component having a current I and a potential difference V. Practice problem 1. Electrical resistors can be made by forming a thin film of carbon on a layer of an insulating material. A carbon film resistor is made from a film of width 8 millimeters and a thickness of 2 micrometers. The diagram shows the direction of the charge flow through the resistor. A. The resistance of the carbon film is 82 ohms. The resistivity of carbon is 4.1 times 10 to the minus 5 ohms times meters. Calculate the length, L, of the film. So to do this, we're going to have to use the equation from topic 5.2. Resistivity equals R times the cross-sectional area over L. So you're given the resistance, you have the length, you know the resistivity or you're looking for length, you know resistivity, so you need to figure out what the cross-sectional area is. And because charge is flowing through here, you need to calculate this area. So it's 2 micrometers by 8 millimeters. Be sure to convert, multiply to get your area, and then you will solve for length. For part B, the film must dissipate a power less than 1500 watts from each square meter of its surface to avoid damage. Calculate the maximum allowable current for the resistor. There are a few equations that we have for power. Power is I times V, or power equals I squared times R, or power equals V squared over R. So based on what we already have, which of these equations do you think will help you calculate the maximum allowable current for the resistor? Part C, the current direction is now changed so that the charge flows vertically through the film. Deduce without calculation the change in the resistance. So think about what changes when we've changed the orientation of the charge flow. Using this equation, resistivity is equal to R times A over L. The material doesn't change. Maybe the length changes, maybe the area changes. How do these changes affect the resistance? An electric circuit is just a set of conductors like wires and components. It could be resistors, lights, LEDs, capacitors, connected to an electrical voltage source like a cell, also known as a battery. They're connected in such a way that this current can flow through all of these components in complete loops. Here are 2 circuits consisting of cells, resistors, and wires. One like this. I can see I have 2 cells, battery 1, battery 2, and 3 resistors. And I can have a battery with 1, 2, 3 resistors wired like this. Current in the cell on the left flows through all of the resistors in a line. Current on the right flows through, it splits between all of these resistors. And note that we draw current from the positive end of the battery to the negative end of the battery. A complete circuit diagram contains a cell or a battery. A schematic of a cell looks like this. A battery is just a series of cells. Then if each cell is 1.5 volts and you have 3 of these in series, you're producing 4.5 volts. Okay, so resistors can be connected in series, which means one after the other. There is only one flow of current, and that current is the same for all series components. Conservation of energy tells us Q times voltage. This symbol, epsilon, is a special symbol that's used for the voltage of a battery. So the symbol here, epsilon, is used for a battery voltage. Q times V is energy. So the energy from the battery has to equal the energy dissipated by each of the resistors. So the current or the charge times the voltage drop for R1 plus the current, the charge times the voltage dropped across R2 plus the charge times the voltage across R3 sums to equal the energy provided by the battery. And all of these charges are the same through R1, 2, 3. They all have to go in a line. They all come from the battery. That's why we can cancel. And this equation then becomes E epsilon equals I times R1 plus I times R2 plus I times R3 from Ohm's law, V equals I times R. If we factor out the I, because they all have the exact same current flow, we have epsilon equals I times R, where R is the sum of the resistors in series. So that's how resistors in series add up. Well, resistors can also be wired in parallel, which means each of the resistors has an independent connection to the battery, or each resistor is directly connected to the battery. That means they all get the same voltage as the battery. If this battery is 9 volts, then there's 9 volts across R1, 9 volts across R2, and 9 volts across R3. But there are 3 currents. There is a current going through R1, R2, and R3, and they may not be equal. They have the same voltage, but they don't necessarily have the same current. The total current, though, that passes through the battery has to equal the sum of all of these currents. If R is the equivalent or total resistance of the 3 resistors, then this sum of these currents becomes voltage over R, which is the total current, equals V1 over R1 plus V2 over R2 plus V3 over R3. Because the voltage is the same across each of the resistors and each of those are identical to the cell, and because we have this relationship from before, we get that V over R, because all of them have the same voltage, equals V over R1 plus V over R2 plus V over R3. We can cancel these voltages. They're the exact same. And we are left with the total resistance. 1 over R equals 1 over R1 plus 1 over R2, etc. Practice number 2. 3 resistors are connected as shown. What is the value of the total resistance between X and Y? So this is an interesting an interesting circuit because you probably haven't seen something represented like this. So the best way is to start either with X or Y. I'm going to start looking at Y and see how the current can travel through this circuit. Anywhere the current can choose a different path, anywhere there's a node or a junction like right here and right here, that is where you're going to have a parallel branch. So follow. I have current traveling like this. The current can split. The current can split right here or it can go here. The current travels. So because between 2 and 3 the current can split, these resistors, I need to label these in order. This is my resistor number, letter A, this is resistor B, and this can be resistor C. That means if the current doesn't have to go through both A and B are in parallel. So resistors A and B are in parallel. Okay, so let's keep following the current as it goes through 3, or resistor B, which is 3 ohms. It can go through here and here again. Okay, so because there is no junction between resistor B and resistor C, that means the current has to travel through both B and C. So B and C are in series. Okay. With that in mind, whenever you're getting the total resistance for a combination circuit like this, where you have both resistors in parallel and in series, you start by getting the total resistance in series first, anything in series. You start with the series resistors, then you combine parallel branches. So I'm going to make resistor B and resistor C into one bigger resistor. So they're in series, that's easy. 3 ohms plus 3 ohms gives me an equivalent resistance for B and C equals 6 ohms. And now it's almost like I have this larger resistor. I could conceptually I could replace this resistor 3 and 3 with just a larger 6 ohm resistor. So this is my theoretical or my conceptual resistor, and this 6 ohm resistor is in parallel with the 2 ohm. So to get the equivalent resistance, or the total resistance, 1 over 6 plus 1 over 2. I will get a common denominator for my 1 over 2. This will be 3 over 6. 3 plus 1 is 4 over 6. But this is the inverse of the answer. So I need to just flip this. And I get 6 over 4, which simplifies to one of the answer choices here. Problems like this are some of my favorite problems because they're not hard, they just require a little bit of math sense. So we have 2 resistors, X and Y, and they're made of uniform cylinders of the same material. X and Y are connected in series. X and Y are of equal length, and the diameter of Y is twice the diameter of X. The resistance of Y is R. So they give me this value. They tell me the resistance of Y is R, which means I'm probably going to end up comparing X to Y. So I want to know, they ask, what is the resistance of this series combination? So I'm going to have to figure out what the resistance of X is and then add that to the resistance of Y. So I've provided this equation up here. The resistance is equal to the resistivity times L over A. So I'm going to write out for R sub Y the equation here, rho times L over the cross-sectional area. This equation I'm going to compare with an equation I make for R sub X, and then I can see how things change based on things that might have been given in the problem that tell me how this equation for the resistance for the X changed. So first thing, compared to the resistivity of Y, what is the resistivity of X? It would be the same because, as noted right here, they're made of the same material. So the resistivity does not change. Whoops. I'll do this in blue so it's a different color. Okay. Now let's compare the length. Oh, it tells me X and Y are of equal length, so the length doesn't change between these two equations. Now I'm going to divide by the area. So I don't know, it tells me the diameter of Y is twice the diameter of X. That is going to affect the area of X compared to the area of Y. So the area of the cross-sectional area of a cylinder is a circle, and a circle has an area of pi r squared. But they give me information about the diameter. Well, r is the radius of a circle is the diameter divided by 2. So just allow me to expand R sub y equation. I'm going to replace a with pi r squared because the cross-sectional area is pi r squared. And then I'm going to go one step further and I'm going to replace r squared in my R sub y equation with d over 2. And let's see how that looks. Now if I square r, I have to square both the d and the 2. So don't forget that. So d, the diameter over 2 squared. Okay? All right. Since the diameter of y is twice the diameter of x, that means the diameter of x is 1/2 the diameter of y. So for the area equation down here, for r sub x, I'm going to write pi times diameter over 2 divided by 2 squared. I can reduce this further or simplify this weird looking fraction further. Diameter over 2 divided by 2 means 1/4. 1/4 of the radius. So this then just becomes diameter over 4. And this I've done to make my comparisons between r sub y and r sub x. So now it should be really clear. I will further simplify the denominator for r sub y so I can see how that looks. R sub y becomes rho times L over pi d squared divided by 4 squared, but that 4 will come all the way up. Sorry, 2 squared, which is 4. So the 4 comes all the way up, 4 rho times L over pi times d squared, and they are representing this value 4 rho times L just as in terms of r. Okay, so now I'm going to square the 16 for r sub x, and this or square the 4 to get 16. 16 rho times L over pi d squared. R is 4 rho L over pi d squared. So r sub x is 4 times that. So r sub x is 4 times r. So now I'm just left with adding these two up to get the total resistance, and you should see the answer is D, 5 times R. Ideal voltmeters, infinite resistance. Okay, so voltmeters are connected in parallel. Voltmeters are set up to read the voltage only of the component it's parallel with. So check this circuit. We can see that if I want the voltage across this resistor right here, I set up my voltmeter in parallel with this particular resistor. This green current represents the amount of current needed by the voltmeter to obtain a measurement. The red current is the amount of current the battery supplied to the original circuit. So because you don't want your voltmeter to alter the properties of the circuit, an ideal voltmeter would have an extremely high resistance, like an infinite resistance, to minimize the current it draws from the circuit. And then we have ideal ammeters. An ammeter is a device that measures a current in a circuit. It's connected in series with whatever branch you're trying to measure. The ammeter is supposed to read the current of the original circuit. So in order to not alter original properties of the circuit, for example, the voltage that gets split among these 3 resistors, you need to have ammeters with extremely low resistance, 0 ohms, to minimize the effect on the red current. A cell with negligible internal resistance is connected as shown. The ammeter and the voltmeter are both ideal. What changes occur in the ammeter reading and in the voltmeter reading when the resistance of the variable resistor is increased? So the variable resistor is this thing right here that is connected to the voltmeter. So the easy one to get first is the change in the ammeter reading. I know that the voltage supplied by the cell is not going to change. Epsilon is constant. And whatever voltage supplied by the cell is V is equal to I times R. So epsilon equals I times R. So if the resistance then increases, epsilon over R, that means current has to decrease. The bigger the R, the smaller the amount of current. So I can eliminate choices A and choice B. Those don't make sense. So now we're left with figuring out whether or not the voltmeter reading is going to increase or decrease. Okay, voltage dropped across this variable resistor. V equals I times R. So yes, the current has dropped across this in this circuit, but at the same time, the resistance value has increased, and it's greater than the resistance of its neighbor. So the larger the resistance of a resistor, the more voltage it dissipates. And because the voltage is split between this guy, this one over here, and the variable resistor, I know that my variable resistor having a larger resistance is going to get a bigger share of the voltage drop. It's going to dissipate more voltage or drop off more voltage. So at the same time, the ammeter reading decreased, but the voltmeter reading increased. So let's say we have a battery that puts out 6 volts, but we have a light bulb or any type of component that can only use 3 volts. How do we get just 3 volts from a 6-volt battery? Well, the best way to do that is to assemble a potential divider, which is a circuit made of 2 or more series resistors that allows us to tap off any voltage that we want that is less than the battery voltage. So the input voltage is the EMF of the cell. The output voltage is the voltage dropped across the second resistor. And again, the total resistance for any series circuitry, for resistors in series is the sum of those values. So from Ohm's law, the current I of the divider is given by the input voltage over the total resistance. And again, the total resistance is the sum of R1 and R2. But the output voltage is just the voltage across the second resistor, and that's I times R times the resistance of the second resistor. So the output voltage is just I times the second resistor value. And the second resistor value times the input voltage divided by R1 plus R2 equals the output voltage. So this is an equation for a potential divider. You might consider adding this to your data booklet. That way it can help you on future exams. In the circuit shown, the fixed resistor has a value of 3 ohms, and the variable resistor can be varied between 0 ohms and 9 ohms. The power supply has an EMF of 12 volts and negligible internal resistance. What is the difference between the maximum and minimum values of voltage across the 3 ohm resistor? So I would start by figuring out what would be the maximum voltage. The maximum voltage would be where the variable resistor has no ohms. So the voltage then dissipated across the 3 ohm resistor would be the entire 12 volts. This would be the maximum. Now, things change if this second resistor is switched to 9 ohms. So when the 9 ohm resistor is set, we first get the total resistance. The equivalent resistance is 3 plus 9 ohms, which gives us 12 ohms, which means the current going through the circuit, I, is V over R, 12 volts over 12 ohms, gives us 1 ampere. So to find out the voltage dropped across the 3 ohm resistor, the voltage across the 3 ohm resistor, I take the current that I just calculated, this 1 amp, and I multiply by the value of the resistor, 3 ohms, which gives me 3 volts lost across the 3 ohm resistor. Likewise, 9 volts would be dropped across here. So the difference between 12 volts, its max, 3 volts, its min, is guess what? 9 volts. Question number 6. The diagram shows a potential divider circuit used to measure the EMF of a cell X. Both cells have negligible internal resistance. Part A. State what is meant by EMF of a cell. Well, EMF is voltage, and if you look in topic 5.1, you can see that voltage is energy per charge. So EMF is the energy required or supplied, energy supplied per charge particle in moving these charges, from one end of the battery to the other. So it's the energy that it takes to move each charge around a circuit from one of the battery's terminals to the other. For part B, AB is a wire of uniform cross-section and length 1 meter. The resistance of wire AB is 80 ohms. When the length of AC is 0.35 meters, the current in cell X is 0. Show that the resistance of the wire AC is 28 ohms. Okay, so I have 12 volts supplied by the cell, and the resistance of the entire wire A sub B is 80. When I've shortened the length of this 1 meter long wire to 0.35 meters, I'm changing the resistance by that same amount. So I've reduced the length to 35% of its original value. So if I reduce the original 80 ohms by 35%, because resistance is proportional to length, I should get 28 ohms. So let's see, we'll do 80 ohms times 0.35. Do we get 28 ohms? Yes, we do indeed. We get 28 ohms. And again, I'm just taking advantage of the fact that length is proportional to resistance. If I've reduced the length from 1 meter to 0.35 meters, I've reduced the length by 65%, which means I've reduced the resistance by 65%. Okay, now we're tasked with determining the EMF of cell X. And if you remember, or you can read in part B, it states that when AC, the length AC is 0.35 meters, no current flows through cell X. What's happening for cell X is that this length A to C is just resistive enough such that cell X cannot overcome the resistance from A to C to allow current to travel through it. We're at the cusp right here, right at C, where no current is flowing through cell X, which can be very helpful because that allows us to determine what the voltage of cell X is. So first things first, we need to figure out how much current flows through the left side. How much current is coming out of the positive 12-volt battery, traveling through A to B, and then coming to the negative end. And we can do that using Ohm's law. 12 volts divided by 80 ohms gives a current of around 0.15 amps on the left side. This potential divider circuit, the position A to C has been chosen because if we were to reposition maybe a little bit lower, maybe right here, current would flow through the circuit, and this position C is the limit where no current is flowing through the circuit. That means that right at this point C, we have managed to match the potential difference C to A, this delta V, with the potential with the EMF supplied by the cell. So when I have 0.15 amps of current flowing across A to C, there is a potential drop from A to C. I've used the 12-volt battery, and I can measure how much current is dropped from A to C, knowing that the resistance from A to C, which we calculated before, was 28 ohms. So the potential difference from A to C matches the potential of cell X. Because they're equal, the cell X doesn't have enough energy per charge to drive these charges around in a circuit. Hopefully that makes sense to you why this cell has been, or this circuit has been set up the way it's been set. So I can take the 0.15 total amps of current going from A to B, and if I multiply this current by the resistance from A to C, it tells me the potential difference, the voltage drop from A to C. That voltage drop then matches the EMF of the cell. So The EMF of the cell is 0.15 amps. That is the total current going through from A to C times the resistance from A to C, and you should get your answer in volts. Okay, we're going to draw a circuit diagram to show how we can measure the resistance of a carbon film resistor using a potential divider arrangement to limit the potential difference across with the target resistor. Start by drawing my battery, one long terminal for the positive, one short terminal for the negative. And we have a wire coming up from positive connecting to our potentiometer, which is a variable value resistor. To make it variable, I connect almost like in series, or actually this is a parallel arrangement. I connect this target, my carbon film resistor, in parallel to the potentiometer. This potentiometer continues connected to the negative terminal. And so what happens inside of the potentiometer is the current could split. I'll finish drawing the circuit and then I'll go more into greater detail. In series with my target carbon film resistor, I'll have an ammeter, and the ammeter connects back to this junction, and in parallel just with my target resistor, I will have a voltmeter. Okay, so here is my carbon film resistor connected in series with an ammeter with a voltmeter connected in parallel across. And then I have the variable resistor, the potentiometer, up here. Inside the potentiometer, you can imagine we could have current coming out of the positive terminal of the battery. Then in here, the current could split, coming either along this way or continuing straight through. The amazing thing is, if I slide this arrow, this wire up, as I slide this up, that decreases the total resistance for this branch here. So the total resistance decreases, so the voltage dropped across here increases. So more voltage is dropped as I reduce the length, as I reduce this length here. When I slide this yellow arrow down, it increases the voltage. So let me draw that again. Changing colors on me. Okay, when I slide this yellow highlighted wire down this way, the voltage drop across what I've colored this green carbon resistor, the voltage across the carbon film resistor decreases. More of the voltage then is dissipated through the length of the potentiometer. So this arrangement, you need to draw it as I've drawn it because I think this is the best way of representing it. This arrangement has a battery connected first to a potentiometer, which you draw like a square, connected to an arrow, and then an arrow connects to a second resistor, wired in series with an ammeter, connected to a junction here that I just managed to erase. Okay, connected here at this junction, and then a voltmeter running across your target carbon film resistor. Number 8, a heater in an electric shower has a power of 8.5 kilowatts when connected to a 240 volt electrical supply. It is connected to the electrical supply by a copper cable. The following data are available. Length of the cable 10 meters, cross-sectional area of the cable 6 millimeters, resistivity of copper 1.7 E negative 8 ohm meters. Calculate the current in the copper cable. So to do this, I can note that I have voltage of the power supply. I have the power consumed by the electric shower. So I can use this equation to get the current. P equals I times V. Part B, calculate the resistance of the copper cable. For this, you need to use the resistivity equation. Part C, explain in terms of electrons what happens to the resistance of the cable as the temperature of the cable increases. As temperature increases, the vibrational energy of the electrons increases. It becomes more difficult for the electrons to move through the circuit because they're moving in a more chaotic nature. And part D, this is for 5 bonus points. The heater changes the temperature of the water by 35 Kelvin. The specific heat capacity of water is 4,200 joules per kilogram per Kelvin. My apologies for that typo, joules per kilogram per Kelvin. Ooh. Okay. Determine the rate at which water flows through the shower. State an appropriate unit for your answer. So this is going to be applied to your exam, both sections, the open-ended and the multiple choice, plus 5 points. Let's see if you can do it. You will need to relate this 8,500 watts to this information given about water, and note that rate has particular units. You need to include that, and you need to think about what type of units or what rate would be associated with the flow of water. I hope you found this video helpful. Thanks for watching, and come to class prepared.